Picture this. You're 8 years old, lying on your back in the grass on a summer night, staring up at the star-filled sky. The Milky Way stretches across the darkness like spilled glitter, and suddenly your mind starts to wander. You begin to imagine traveling upward, past the clouds, past where aeroplanes fly, past the moon and the sun, past all the stars you can see. And then, inevitably, that question hits you like a cosmic thunderbolt. But where does it all end? If you've never had this thought, you're either lying or you haven't been paying attention to the universe around you. This question is so fundamental to human curiosity that it's practically hardwired into our brains. We're creatures that evolved in a world of boundaries and edges. Every forest has a clearing. Every ocean has a shore. Every room has walls. Our entire experience tells us that everything must have limits, borders, places where one thing stops and another begins. But here's what makes this question so deliciously maddening. It's not just a childhood wonder that we outgrow. Some of the greatest minds in human history have wrestled with this exact same puzzle. Einstein himself spent sleepless nights contemplating the nature of space and its potential boundaries. When he developed his theories of relativity, he wasn't just solving abstract mathematical problems, he was trying to understand the very fabric of reality, including whether that fabric has edges. The question, where does space end, has a peculiar quality that sets it apart from almost every other question we might ask. When we wonder about other boundaries, like where does the Amazon rainforest end, or where does the Pacific Ocean end, we have a clear mental framework for thinking about the answer. The rainforest ends where it meets grassland or cities. The ocean ends where it meets the shore. But when we try to apply this same logic to space itself, our brains start to short-circuit. Think about it. If space ends somewhere, what's on the other side of that boundary? More space? But then that wouldn't really be the end, would it? Maybe there's a wall, like the edge of a cosmic room. But what's the wall made of? And what's behind the wall? Nothing? But how can there be nothing somewhere? Even nothing is something. It's the absence of something, which means there's still a somewhere for that absence to exist. This is where most people's brains start to feel like they're melting, and honestly, that's exactly the appropriate response. We're bumping up against one of the fundamental limitations of human cognition. Our brains evolved to navigate a world of medium-sized objects at medium speeds across medium distances. We're exquisitely tuned to understand things like the watering hole is behind that hill, or the predator is approaching from the left. We were never meant to conceptualize infinity, to truly grasp the implications of endless space, or to understand what it means for something to have no boundary at all. Yet here we are, these peculiar creatures with brains that can barely comprehend their own limitations, trying to understand the ultimate nature of reality. It's simultaneously humbling and remarkable. We're like ants trying to understand the internet. We might be able to grasp little pieces of it, but the full scope is so far beyond our natural cognitive abilities that we have to use tools, mathematics, and careful reasoning to even begin to approach the truth. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." But perhaps he should have added a caveat. It's comprehensible to a point, and then it becomes so strange, so removed from our everyday experience, that we have to stretch our minds to the breaking point just to glimpse the edges of understanding. Before we can even begin to explore where space might end, we need to do something that most people skip over. We need to be extremely careful about what we mean when we ask this question.
This might seem like unnecessary philosophical nitpicking, but I promise you, this clarity is absolutely essential. Without it, we'll end up chasing our tails and confusing ourselves even more than we already are. When someone asks, "Where does space end?" they might actually be asking one of several completely different questions, each with its own answer. It's like asking, "Where does the ocean end?" Are you asking where the water meets the beach, where you can't see any further from your current position, or whether there's actually a final drop of water somewhere beyond which no more ocean exists? Let's untangle these different meanings, because each one will take us down a completely different rabbit hole of understanding. First, there's what we might call the atmospheric boundary interpretation. Some people, when they ask where space ends, are really asking where our planet's atmosphere ends and space begins. This is actually the most straightforward version of the question, and it has a relatively simple answer. Most scientists define the boundary of space as the Kármán line, which sets about 100 kilometers above Earth's surface. Above this altitude, the atmosphere becomes so thin that conventional aircraft can't generate enough lift to fly, and spacecraft can orbit without being slowed down by atmospheric drag.
But here's the thing, even this seemingly simple boundary isn't really a hard edge. The atmosphere doesn't just stop at 100 kilometers like hitting a wall. Instead, it gradually thins out over hundreds of kilometers, becoming progressively more sparse until it's virtually indistinguishable from the vacuum of space. It's more like the way a beach slopes into the ocean. There's no single line where you can definitively say, here's where the land ends and the water begins. The second interpretation is what we might call the observational boundary question. This is asking, how far out can we see and what lies at the limit of our vision? This is where things start to get really interesting, because the answer involves some of the most mind-bending concepts in all of physics. We can see out to what astronomers call the observable universe, a sphere centered on Earth with a radius of about 46.5 billion light-years. But here's the crucial point. This boundary isn't a wall or an edge of space itself. It's simply the limit of what we can observe from our particular vantage point in the cosmos. Think of it this way. Imagine you're standing in a dense fog that limits your visibility to exactly 100 meters in any direction. You can see trees, rocks, and other objects within that 100-meter circle, but beyond that, everything disappears into gray obscurity. Now, does the fact that you can't see beyond 100 meters mean that the world ends at that distance? Of course not. It just means that your ability to gather information about the world is limited by the fog. The observable universe is remarkably similar. The fog, in this case, is the finite age of the universe combined with the finite speed of light. Light from very distant objects simply hasn't had enough time to reach us yet, so we can't see what lies beyond our cosmic horizon. And just like in the fog analogy, the fact that we can't see beyond this boundary doesn't mean that space itself ends there. But this leads us to the third and most profound interpretation of our question. Does space itself, not just our ability to observe it, but the actual fabric of reality, have an edge or boundary somewhere? This is the question that kept Einstein awake at night, and it's the one that will occupy most of our exploration. This version of the question is asking about the ultimate nature of reality itself. Is the universe finite in size, like a cosmic sphere or box, with actual edges beyond which there is simply nothing? Or does space extend infinitely in all directions, meaning that no matter how far you travel, there's always more space ahead of you? Or, and this is where things get really wild, might space be finite but without boundaries, curved back on itself in ways that our three-dimensional minds can barely conceive? To understand why this question is so challenging, we need to grapple with a fundamental limitation of human experience. We have never encountered anything truly infinite in our daily lives. Every object we've ever seen has had boundaries. Every journey we've ever taken has had a starting point and a destination. Every container we've ever used has had walls, a bottom, and a top. But infinity isn't just really, really big. It's not like the difference between a puddle and an ocean, or between a pebble and a mountain. Infinity is qualitatively different from any finite quantity, no matter how large. If space is infinite, then it contains an infinite number of stars, an infinite number of galaxies, an infinite number of planets. In fact, if space is infinite, and matter is distributed roughly evenly throughout it, then somewhere out there, separated by an incomprehensibly vast distance, there's another planet, exactly like Earth, with another person, exactly like you, reading these exact same words.
This isn't science fiction, it's a logical consequence of infinite space combined with quantum mechanics. In an infinite universe, every possible arrangement of matter that can exist will exist, not just once, but infinitely many times. There are infinite versions of you making slightly different choices, infinite Earths where history unfolded differently, infinite variations on every theme imaginable. On the other hand, if space is finite, if there really is an edge somewhere, then we're faced with equally mind-bending questions. What exists beyond that edge? Is it possible for there to be a beyond when we're talking about the boundary of space itself? These questions quickly push us into philosophical territory where the distinction between physics and metaphysics becomes blurry.
Now, let's dive deeper into that second interpretation, the question of how far we can see and what that tells us about the nature of space. Understanding the observable universe is crucial because it's the only part of the cosmos that we can study directly, and yet it reveals profound truths about the nature of reality that extend far beyond what we can observe. The story begins with a number that's become famous in cosmology: 13.8 billion years. This is the approximate age of our universe, the time that has elapsed since the Big Bang. Now, you might think that this means we can see out to a distance of 13.8 billion light-years in any direction. After all, that's how far light has had time to travel since the beginning of everything, right? But here's where the universe starts playing tricks on us, demonstrating that reality is far more subtle and strange than our intuitions suggest. The actual distance to the edge of the observable universe is about 46.5 billion light-years, not 13.8 billion. How is this possible? How can we see objects that are farther away than light has had time to travel? The answer lies in one of the most important and counterintuitive concepts in modern cosmology: the expansion of space itself. When we say that the universe is expanding, we don't mean that galaxies are flying apart through empty space like fragments from an explosion. Instead, we mean that space itself, the very fabric of reality, is stretching and growing.
To understand this, imagine an ant walking across the surface of a balloon while you're inflating it. From the ant's perspective, it's walking at a steady pace in a straight line. But from your perspective, watching the balloon expand, the ant is being carried along by the stretching surface even as it walks.
The distance between the ant and any fixed point on the balloon is increasing not just because the ant is walking, but also because the balloon itself is growing. The same thing happens with light traveling through expanding space. A photon of light emitted from a distant galaxy 13 billion years ago has indeed been traveling toward us for 13 billion years. But during that entire journey, space has been expanding, carrying that galaxy farther and farther away from us. By the time the photon reaches our telescopes today, the galaxy that emitted it is now about 46 billion light-years away. This expansion of space creates what cosmologists call the cosmic horizon, a boundary beyond which we simply cannot see, not because there's nothing there, but because light from those regions hasn't had enough time to reach us yet. It's important to understand that this horizon is not a physical boundary in space. It's more like a temporal boundary, a limit imposed by the finite age of the universe and the finite speed of light. But here's where things get even more interesting. This horizon is constantly expanding. Every second that passes, light from slightly more distant regions of the universe has enough time to reach us, pushing our observable horizon a little bit farther out. We're constantly receiving first light from regions of space that have never been visible before in the history of our universe.
However, there's a twist to this story that reveals something profound about the nature of cosmic expansion. While our horizon is expanding, the expansion of space itself is accelerating, driven by a mysterious force that we call dark energy. This means that galaxies beyond a certain distance are being carried away from us so rapidly by expanding space that their light will never be able to reach us, no matter how long we wait. Think about this carefully. There are regions of space that exist right now, filled with stars and galaxies and possibly even other forms of life, but they are forever beyond our ability to observe or communicate with. From our perspective, these regions might as well be in a completely separate universe. The accelerating expansion of space has created a cosmic horizon that permanently separates us from vast portions of reality. This realization has profound implications for how we think about our place in the cosmos. We often imagine ourselves as being at the center of a vast but ultimately knowable universe, where patient observation and clever technology might eventually reveal all of the cosmos's secrets. But the reality is far more humbling. We inhabit a small, observable bubble in what might be an infinitely vast ocean of space and time, most of which will forever remain beyond our reach.
The observable universe reveals another crucial concept, the cosmic microwave background radiation, which represents the farthest back in time that we can directly observe. This radiation is the afterglow of the Big Bang, emitted about 380,000 years after the beginning of time, when the universe first became transparent to light. Before this moment, the universe was so hot and dense that photons couldn't travel very far without being absorbed or scattered by free electrons. It was like trying to see through a thick fog. When we observe the cosmic microwave background, we're seeing our universe as it existed when it was just a baby, a mere 380,000 years old compared to its current age of 13.8 billion years. This radiation carries information about the conditions in the early universe, including tiny temperature variations that eventually grew into the large-scale structure of galaxies and galaxy clusters that we see today. But beyond this wall of radiation lies what cosmologists poetically call the dark ages of the universe. a period when space was filled with neutral hydrogen gas but had not yet formed the first stars and galaxies. We cannot directly observe this era because there were no sources of light, but we can infer what must have happened based on our understanding of physics and the evidence we see in the cosmic microwave background.
The existence of the cosmic microwave background also tells us something important about the nature of space beyond our observable horizon. This radiation appears remarkably uniform across the entire sky. Its temperature varies by only tiny amounts from one direction to another. This uniformity suggests that the entire observable universe was once in thermal equilibrium, meaning that different regions were once close enough together to exchange energy and reach the same temperature. But here's the puzzle. According to our understanding of cosmic expansion and the finite speed of light, regions on opposite sides of our observable universe should never have been able to communicate with each other. They should never have been close enough to reach thermal equilibrium. It's like finding that two people on opposite sides of the Earth are wearing exactly the same unique outfit despite never having met or communicated. This puzzle, known as the horizon problem, provides our first hint that the observable universe might be just a tiny fraction of a much larger reality. The solution to this problem involves one of the most extraordinary ideas in all of cosmology: cosmic inflation, a period in the very early universe when space expanded faster than the speed of light, growing from smaller than a subatomic particle to larger than a grapefruit in an infinitesimally small fraction of a second. If cosmic inflation really happened, and the evidence strongly suggests that it did, then our entire observable universe, everything we can see or will ever be able to see, represents just a tiny patch in a vastly larger space that was created during this period of explosive expansion. The regions that appear disconnected to us today were once close neighbors before inflation stretched them apart.
This brings us to the edge of one of the deepest mysteries in cosmology. If our observable universe is just a small bubble in this inflated space, what lies beyond our cosmic horizon? Is space finite or infinite? Does it have boundaries? And if so, what exists beyond those boundaries? Are there other regions, perhaps with different physical laws, different numbers of dimensions, or even different ways that matter and energy behave? These questions push us beyond the realm of direct observation and into the territory of theoretical physics and mathematical inference. But they're not idle speculation. They're the natural consequences of taking our best scientific theories seriously and following them to their logical conclusions.
If you've ever tried to piece together a jigsaw puzzle without seeing the picture on the box, you know how challenging it can be to understand what you're building until the image starts to emerge. Cosmologists face a similar challenge when trying to understand the universe, except their puzzle has trillions of pieces spread across billions of light years, and many of the most important pieces are invisible or existed billions of years ago. Fortunately, the universe has provided us with something extraordinary, a cosmic baby picture that shows us what everything looked like when the cosmos was just 380,000 years old. This baby picture is called the Cosmic Microwave Background Radiation, or CMB, and it's arguably the most important discovery in modern cosmology. Understanding this radiation is crucial to grasping how we know what we know about space and its potential boundaries. To understand what the cosmic microwave background represents, we need to travel back in time to the very early universe, when conditions were so extreme that they would make the core of the sun seem like a pleasant spring day. In the beginning, the universe was unimaginably hot and dense, so hot that atoms couldn't even exist. Instead, space was filled with a seething plasma of protons, electrons, and photons, all bouncing around in a cosmic soup. Think of this early universe as being like the inside of a star, where the temperature is so high that electrons can't settle into stable orbits around atomic nuclei. Instead, they zip around freely, constantly colliding with photons of light. In this state, light couldn't travel very far before being absorbed or scattered by a free electron. It was as if the entire universe was shrouded in an impenetrable fog.
This situation persisted for the first 380,000 years after the Big Bang. During this time, the universe was expanding and cooling, but it remained opaque to light. Any photon that tried to travel across space would quickly encounter a free electron and be scattered in a random direction. If you had somehow existed during this era and tried to look around, you wouldn't have been able to see anything beyond a few inches, despite the fact that space was filled with an intense glow. But then something remarkable happened. As the universe continued to expand and cool, the temperature dropped to a critical threshold, about 3,000 degrees Celsius. At this temperature, electrons finally had little enough energy that they could be captured by protons to form the first hydrogen atoms. This event, which cosmologists call recombination, was one of the most important transitions in cosmic history. When recombination occurred, the universe suddenly became transparent. With most of the free electrons now bound up in atoms, photons could finally travel freely across space without being constantly scattered. The cosmic fog lifted, and for the first time in the universe's history, light could stream unimpeded across vast distances. The photons that were released during recombination have been traveling through space ever since, carrying with them a snapshot of what the universe looked like at that crucial moment. These ancient photons fill all of space around us right now. In fact, there are about 400 of these relict photons in every cubic centimeter of space, including the space between your eyes and this screen. However, there's something we need to understand about these ancient photons. When they were first released 13.8 billion years ago, they were extremely hot, glowing with the intense heat of the 3,000-degree plasma from which they emerged. If you could have seen this light when it was first released, it would have appeared as a brilliant orange-red glow, similar to the light emitted by molten metal.
This situation persisted for the first 380,000 years after the Big Bang. During this time, the universe was expanding and cooling, but it remained opaque to light. Any photon that tried to travel across space would quickly encounter a free electron and be scattered in a random direction. If you had somehow existed during this era and tried to look around, you wouldn't have been able to see anything beyond a few inches, despite the fact that space was filled with an intense glow. But then, something remarkable happened. As the universe continued to expand and cool, the temperature dropped to a critical threshold, about 3,000 degrees Celsius. At this temperature, electrons finally had little enough energy that they could be captured by protons to form the first hydrogen atoms. This event, which cosmologists call recombination, was one of the most important transitions in cosmic history. When recombination occurred, the universe suddenly became transparent. With most of the free electrons now bound up in atoms, photons could finally travel freely across space without being constantly scattered. The cosmic fog lifted, and for the first time in the universe's history, light could stream unimpeded across vast distances.
The photons that were released during recombination have been traveling through space ever since, carrying with them a snapshot of what the universe looked like at that crucial moment. These ancient photons fill all of space around us right now. In fact, there are about 400 of these relic photons in every cubic centimeter of space, including the space between your eyes and this screen. However, there's something we need to understand about these ancient photons. When they were first released 13.8 billion years ago, they were extremely hot, glowing with the intense heat of the 3,000-degree plasma from which they emerged. If you could have seen this light when it was first released, it would have appeared as a brilliant orange-red glow, similar to the light emitted by molten metal.
But remember, space has been expanding for the entire 13.8 billion years that these photons have been traveling toward us. As space expands, it stretches the wavelengths of all the light passing through it, making the light appear redder and cooler. This process, called cosmological red shift, has stretched those originally hot orange photons until they now appear as microwave radiation, the same type of electromagnetic waves used in microwave ovens, though much weaker. This is why we call it the cosmic microwave background. The background part refers to the fact that this radiation comes to us from all directions in space, forming a backdrop behind all the stars and galaxies we can see. The microwave part tells us about the current wavelength of this ancient light, stretched by billions of years of cosmic expansion. You can actually detect this radiation with surprising ease. If you have an old television with rabbit ear antennas, about 1% of the static you see when you tune to an empty channel is caused by cosmic microwave background photons hitting the antenna. You're literally seeing the afterglow of the Big Bang on your TV screen.
But it wasn't until the 1960s that scientists first discovered this radiation, and when they did, it was completely by accident. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a sensitive radio antenna to study radio waves from our galaxy. However, they kept detecting an annoying background noise that seemed to come from all directions equally. They initially thought this might be caused by pigeon droppings on their antenna, but even after cleaning away the droppings and trying everything else they could think of, the signal persisted. What they had actually discovered was the first direct evidence of the Big Bang theory. This uniform background radiation was exactly what cosmologists had predicted should exist if the universe had begun in a hot, dense state and then expanded and cooled over billions of years. The discovery earned Penzias and Wilson the Nobel Prize and provided crucial support for our modern understanding of cosmic evolution.
But the cosmic microwave background is much more than just evidence for the Big Bang. It's also a treasure trove of information about the early universe, encoded in tiny variations in temperature across the sky. When we measure the CMB with sensitive instruments, we find that it's not perfectly uniform. Instead, there are tiny hot and cold spots, temperature variations of only about 0.00001 degrees, scattered across the cosmic background. These tiny temperature fluctuations might seem insignificant, but they represent the seeds from which all the large-scale structure in the universe grew. The slightly warmer regions corresponded to areas where matter was slightly denser than average, while the cooler regions had slightly less matter. Over hundreds of millions of years, gravity amplified these tiny density variations, causing matter to clump together in the denser regions and creating the cosmic web of galaxies and galaxy clusters that we see today. Think of it this way.
The cosmic microwave background is like a topographical map of the early universe, showing us the landscape of tiny hills and valleys in the density of matter that would eventually grow into the mountains and canyons of cosmic structure. Every galaxy cluster, every void, every large-scale structure in the modern universe can trace its ancestry back to these minute temperature variations in the cosmic microwave background. Modern satellites, like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory, have mapped these temperature variations with exquisite precision, creating detailed pictures of the universe as it existed when it was less than 400,000 years old. These maps have allowed cosmologists to measure fundamental properties of the universe with unprecedented accuracy, including its age, its composition, and even its geometry. The cosmic microwave background has also revealed something puzzling that brings us back to our central question about the nature of space. When we look at this ancient radiation from opposite sides of the sky, we find that it has almost exactly the same temperature everywhere. This uniformity is remarkable and tells us that the entire observable universe was once in thermal equilibrium. But here's where the puzzle becomes apparent. Light from opposite sides of our observable universe has traveled for nearly 14 billion years to reach us. This means these regions are now separated by about 28 billion light-years, accounting for the expansion of space. According to our understanding of cosmic expansion, these regions should never have been close enough to exchange heat and reach the same temperature. They should never have been able to communicate with each other at all. It's like finding that two cities on opposite sides of the Earth have exactly the same temperature, despite having no way to exchange heat or information. This uniformity shouldn't exist if the universe had always been expanding at the rate we observe today. The fact that it does exist tells us that something extraordinary must have happened in the very early universe to create this uniformity before normal expansion began.
Let's dive deeper into this puzzle, because understanding it is crucial for grasping how we know that our observable universe might be just a tiny fraction of a much larger reality. This problem, which cosmologists call the horizon problem, represents one of the most important clues we have about the true nature of space and its extent. To understand the horizon problem, we need to think carefully about what it means for different regions of space to be in thermal equilibrium, that is, to have the same temperature. When two objects have different temperatures, heat flows from the warmer object to the cooler one until they reach the same temperature. This process requires some form of communication or connection between the objects, whether it's through direct contact, radiation, or some other means of energy transfer. In the context of the early universe, thermal equilibrium means that different regions of space were able to exchange energy and reach the same temperature. But for this to happen, these regions must have been close enough together that light could travel between them in the time available. This is where the concept of a horizon becomes important. In cosmology, a horizon represents the maximum distance that light can travel in a given amount of time. Just as your horizon on Earth represents the farthest distance you can see because of the curvature of the planet, a cosmic horizon represents the farthest distance that light could have traveled since some particular moment in time.
Now let's do some cosmic accounting. At the time when the cosmic microwave background was emitted about 380,000 years after the Big Bang, light had only had 380,000 years to travel and establish thermal equilibrium between different regions. In that time, light could travel at most 380,000 light-years, which sounds like a lot until you consider the scale of the observable universe. But here's the crucial point. Because space has been expanding ever since the Big Bang, those regions that were 380,000 light-years apart when the CMB was emitted are now separated by much larger distances. When we account for the expansion of space over the past 13.8 billion years, regions that were just barely in causal contact when the CMB was emitted are now separated by about 2 degrees on our sky. This means that when we look at the cosmic microwave background, regions that are more than 2 degrees apart on the sky should never have been able to communicate with each other. They should never have been able to exchange heat and reach thermal equilibrium. Yet, when we measure the temperature of the CMB across the entire sky, we find that it's uniform to within 0.00001 degrees everywhere we look. To put this in perspective, imagine that you wake up one morning to discover that every thermometer on Earth reads exactly the same temperature down to the 5th decimal place. You check the temperature in New York, in Tokyo, in Antarctica, and in the Sahara Desert, and they're all identical. This would be completely impossible under normal circumstances, because these locations have no direct way to exchange heat with each other. The uniformity of the cosmic microwave background presents exactly this type of impossible situation, but on a cosmic scale. We're seeing regions of the early universe that should never have been able to communicate with each other. Yet they all have exactly the same temperature. This is the horizon problem, and it was one of the major puzzles in cosmology for many years.
The problem becomes even more severe when we consider larger angular scales. Regions of the CMB that are separated by more than a few degrees on the sky correspond to parts of the early universe that were so far apart they couldn't even have been aware of each other's existence. Yet these regions all show the same temperature to extraordinary precision. Think about what this implies. If different regions of the universe had started with slightly different temperatures, densities, or other properties, we would expect to see large variations in the cosmic microwave background. Some areas should be much hotter than others, some should have different amounts of matter, and the overall picture should be quite chaotic and non-uniform. Instead, we see a universe that appears to have been set up with incredibly precise initial conditions. Conditions so finely tuned that every region, no matter how distant from every other region, started with almost exactly the same properties. This level of uniformity seems to require an extraordinary coincidence, unless something happened to create this uniformity. The horizon problem isn't just an academic curiosity. It has profound implications for our understanding of the nature of space itself. If the universe had always expanded at the rate we observe today, then the uniformity we see in the cosmic microwave background would be impossible to explain without invoking some kind of incredible fine-tuning of initial conditions.
But there's another aspect of the horizon problem that's even more mind-bending. The problem isn't just that distant regions of the universe have the same temperature. It's that they have the same temperature to such extraordinary precision. The cosmic microwave background varies by only about 0.00001 degrees across the entire sky. This level of uniformity is so extreme that it would be like finding that every grain of sand on every beach on Earth has exactly the same size, color, and composition. This precision tells us that whatever process created the uniformity of the cosmic microwave background, it must have been incredibly efficient and thorough. It couldn't have been a gradual process of heat exchange, because there simply wasn't enough time for distant regions to communicate with each other. It must have been something that could establish uniformity across vast regions of space almost instantaneously. The horizon problem also has implications for the fundamental question of whether space is finite or infinite. If space is infinite and has always expanded at the rate we observe today, then most of that infinite space should be completely disconnected from the region we can observe. Different parts of this infinite space should have started with completely different initial conditions, leading to a universe that looks very different from one place to another. But the uniformity we observe suggests that our observable universe was once much more connected than it appears to be today. This points toward a solution that involves a period in the early universe when different regions that are now widely separated were once close neighbors. This is where the concept of cosmic inflation comes into play. However, before we explore inflation, it's worth considering what the horizon problem tells us about the nature of our cosmic observations. When we look out into space, we're not just seeing distant objects, we're seeing into the past. The farther we look, the further back in time we see. This means that our observations of the universe are fundamentally limited not just by distance, but by time.
The cosmic microwave background represents the farthest back in time that we can directly observe, but it also shows us that the universe was already remarkably uniform by that early epoch. This uniformity must have been established even earlier, during a period that we cannot directly observe, because the universe was opaque to light. This brings us to an important realization. The observable universe may not be representative of the universe as a whole. The fact that everything we can see appears uniform and follows the same physical laws may simply be because we're observing a region that was processed by whatever mechanism created this uniformity. Beyond our observable horizon, there may be regions with very different properties, different physical constants, or even different numbers of dimensions. The horizon problem thus opens a window into the possibility that our observable universe is just one small patch in a vastly larger and more diverse cosmos. This is one of the key insights that leads cosmologists to consider models of the universe that extend far beyond what we can observe, including scenarios where space might be infinite, or even where there might be multiple universes with different properties. Now we arrive at one of the most extraordinary ideas in all of physics. A concept so radical that when it was first proposed, many scientists thought it was too wild to be taken seriously. Yet, cosmic inflation has become the leading explanation for some of the deepest mysteries in cosmology, including the horizon problem we just discussed. Understanding inflation is crucial for grasping how we know that space might extend far beyond what we can observe. Cosmic inflation proposes that in the first tiny fraction of a second after the Big Bang, space itself underwent a period of exponential expansion that was far more rapid than anything we observe in the universe today.
During this inflationary epoch, space expanded faster than the speed of light, growing from a region smaller than a proton to something larger than a grapefruit in less than 10 to the minus 32 seconds, a time interval so brief that it makes a nanosecond seem like an eternity. To get a sense of just how dramatic this expansion was, consider this analogy. If a single atom suddenly inflated at the same rate that space inflated during this period, it would grow to be larger than our solar system in that same minuscule fraction of a second. This isn't just rapid expansion, it's expansion so fast and so extensive that it defies our everyday understanding of how things can grow or change. But before we explore the implications of inflation, we need to address a crucial point that often confuses people. How can space expand faster than the speed of light? Doesn't Einstein's theory of relativity tell us that nothing can travel faster than light?
The answer lies in understanding exactly what Einstein's speed limit applies to. According to relativity, no object or information can travel through space faster than light. But space itself isn't subject to this limitation. Space can stretch, bend, and expand at any rate without violating relativity, because the expansion of space isn't movement through space, it's the creation of new space itself. Think of it this way. Imagine you're an ant, walking across the surface of a balloon while someone inflates the balloon extremely rapidly. From your perspective as the ant, you're not moving faster than your normal walking speed relative to the surface you're on. But from the perspective of someone watching the balloon expand, you're being carried along by the expanding surface at a rate that could be much faster than your walking speed. The surface itself is expanding, carrying you along with it. During cosmic inflation, space expanded in a similar way. Objects embedded in that space were carried along by the expansion, potentially moving apart from each other faster than light, even though nothing was actually moving through space faster than light. This distinction is crucial for understanding how inflation could solve the horizon problem. The idea of cosmic inflation was developed in the early 1980s by physicist Alan Guth, who was trying to solve several puzzles in cosmology, including the horizon problem. Guth realized that if the universe underwent a period of exponential expansion very early in its history, regions that are now widely separated could have started out close together before inflation began. Here's how inflation solves the horizon problem. Before inflation began, the region that would eventually become our observable universe was much smaller, perhaps smaller than a single proton. At that tiny size, different parts of this region could easily communicate with each other and reach thermal equilibrium. They could exchange heat, energy, and information because they were close neighbors.
Then inflation kicked in, expanding space so rapidly that these regions were suddenly carried far apart. But they retained the memory of their earlier communication. They all kept the same temperature and other properties that they had established when they were close together. It's like taking a group of people who are all talking to each other in a small room, then suddenly expanding the room to the size of a continent while keeping everyone in their relative positions. Even though they can no longer communicate, they all remember the same conversation they were having before the expansion. This elegant solution explains not only why the cosmic microwave background is so uniform, but also why it has exactly the tiny variations that we observe. These variations represent quantum fluctuations that existed in the pre-inflationary region, microscopic variations in density and energy that were stretched to cosmic scales by the inflationary expansion. But inflation does more than just solve the horizon problem. It also explains another major puzzle in cosmology called the flatness problem.
Earlier, we discussed how the geometry of space can be flat, curved like a sphere, or curved like a saddle. Observations show that our universe is remarkably flat, so flat that if it has any curvature at all, that curvature is incredibly slight. Here's why this flatness is puzzling. For the universe to be as flat as we observe today, it must have started out incredibly precisely flat in the beginning. Any significant initial curvature would have been amplified by billions of years of cosmic expansion, leading to a universe that's either dramatically curved like a sphere or dramatically curved like a saddle. The fact that we observe a flat universe suggests that the initial conditions were fine-tuned to extraordinary precision. Inflation solves this problem through a process analogous to blowing up a balloon. If you draw a small triangle on a deflated balloon, the angles of that triangle will add up to something different from 180 degrees because the balloon's surface is curved. But if you inflate the balloon to enormous size, that small triangle will appear flatter and flatter as the balloon expands. From the perspective of an ant living on the triangle, the surface appears perfectly flat even though the balloon as a whole retains its curved shape.
Similarly, inflation stretched space so dramatically that any initial curvature was diluted to the point where our observable region appears flat, even if the universe as a whole might have significant curvature at larger scales. This explains why we observe such a remarkably flat universe without requiring incredibly precise initial conditions. The evidence for cosmic inflation comes from several sources, but one of the most compelling is the pattern of temperature variations in the cosmic microwave background. These variations have exactly the characteristics that inflation predicts. They're nearly scale invariant, meaning they have similar strengths at different angular scales, and they follow a pattern that matches quantum fluctuations stretched to cosmic size. Modern observations have also detected what are called B-mode polarization patterns in the cosmic microwave background, subtle twists in the polarization of the ancient light that are predicted to result from gravitational waves produced during inflation. These observations provide direct evidence that inflation actually occurred and give us information about the energy scales and physical processes involved. But perhaps the most profound implication of cosmic inflation is what it suggests about the extent of space beyond our observable universe. If inflation really happened the way we think it did, then our entire observable universe, everything we can see or will ever be able to see, represents just a tiny patch in a vastly larger inflated region. Think about this carefully. If a region smaller than a proton was inflated to become larger than a grapefruit, and our observable universe came from just a small part of that inflated region, then there must be vast amounts of space beyond our cosmic horizon that underwent the same inflationary expansion. These regions would have the same basic physical laws as our observable universe, but they might have different local properties, different patterns of galaxy formation, or even different outcomes of quantum processes. This realization leads to what cosmologists call the multiverse, the idea that our observable universe is just one region in a vastly larger space that was created by cosmic inflation. Some versions of inflation theory suggest that the inflationary process might never completely end, continuously creating new regions of space with different properties. But inflation raises as many questions as it answers. What caused inflation to begin? What caused it to end in our region while possibly continuing elsewhere? What existed before inflation, and what lies beyond the regions that have undergone inflationary expansion?
These questions push us to the very edges of physics and philosophy, where the distinction between scientific theory and speculation becomes blurry. They also bring us back to our central question about where space ends,
because inflation suggests that the space we can observe might be just an infinitesimal fraction of a much larger and possibly infinite reality. The story of cosmic inflation illustrates something profound about the nature of scientific discovery. Sometimes the solutions to our deepest puzzles require us to consider ideas that seem impossibly strange or radical. The notion that space could expand faster than light, growing from subatomic to cosmic scales in a fraction of a second, violates every intuition we have about how reality should behave. Yet this bizarre idea provides elegant solutions to multiple cosmological puzzles and makes specific predictions that have been confirmed by observations. This suggests that our quest to understand where space ends may require us to be even more open to radical possibilities. The universe has already shown us that reality is far stranger and more wonderful than our everyday experience suggests. As we continue to probe deeper into the nature of space and time, we should be prepared for discoveries that challenge our most basic assumptions about the cosmos and our place in it.
We're now ready to tackle one of the most mind-bending questions in all of cosmology. What is the actual shape of space itself? This isn't asking about the shapes of objects within space, like stars and galaxies, but rather about the fundamental geometry of the cosmic stage on which everything plays out. Understanding this concept is absolutely crucial for grasping whether space has boundaries and what it might mean for space to end. To approach this question, we need to start by expanding our intuition beyond the familiar three-dimensional world we experience every day. Most of us live our entire lives thinking of space as flat and infinite, extending in all directions like an endless grid. This seems so obvious that questioning it feels almost absurd. After all, when you look around, space appears to extend uniformly in all directions, following the familiar rules of Euclidean geometry that we learned in school. But here's where Einstein's revolutionary insights come into play. One of the most profound discoveries of the 20th century was that space isn't just an empty stage where matter performs its cosmic dance. Instead, space itself is a dynamic, flexible medium that can be bent, stretched, and curved by the matter and energy it contains. This realization completely transformed our understanding of gravity and opened up entirely new ways of thinking about the cosmos. Let's start with a thought experiment that will help us understand how space can have different geometries. Imagine you're a two-dimensional being living on a perfectly flat surface, like an infinite sheet of paper. In this flat world, all the familiar rules of geometry work exactly as you'd expect. If you draw a triangle, the angles always add up to exactly 180 degrees. If you draw two parallel lines, they never meet, no matter how far you extend them. If you measure the circumference of a circle and divide by its diameter, you always get pi.
This flat geometry is what mathematicians call Euclidean geometry, named after the ancient Greek mathematician Euclid, who first described its properties systematically. For most of human history, we assumed that the geometry of our universe was Euclidean, because that's what we observe in our everyday experience. When we build houses, the angles of rectangular rooms add up to 360 degrees. When we navigate across the Earth's surface over short distances, straight lines behave exactly as Euclidean geometry predicts. But now imagine that you're a two-dimensional being living on the surface of a sphere, like the surface of a basketball. At first, this curved world might seem identical to the flat world, especially if you can only observe a small region around you. If you're an ant crawling on a basketball, the surface appears perfectly flat from your limited perspective. However, as you begin to explore larger areas and make more precise measurements, you'd start to notice some very strange things. For instance, if you draw a triangle on the sphere's surface, you'd discover that its angles add up to more than 180 degrees. A particularly dramatic example would be to start at the North Pole, travel straight down to the equator, Turn exactly 90 degrees and travel along the equator for a quarter of the way around the sphere, then turn 90 degrees again and travel straight back to the North Pole. You've just drawn a triangle with 3 90-degree angles, giving you a total of 270 degrees instead of the 180 degrees that Euclidean geometry predicts. Similarly, if you try to draw parallel lines on a sphere, you'll find that they eventually curve toward each other and meet. Lines of longitude on Earth provide a perfect example. They start out parallel at the equator, but converge at the poles. This type of geometry, where parallel lines converge and triangles have more than 180 degrees, is called spherical or closed geometry. But there's also a third possibility that's harder to visualize, but equally important. Imagine a surface that curves away from itself, like a saddle or a Pringles potato chip. On this type of surface, triangles have angles that add up to less than 180 degrees, and parallel lines actually diverge from each other as you extend them further. This type of geometry is called hyperbolic or open geometry.
Now comes the crucial leap. Einstein's general theory of relativity tells us that our three-dimensional space can have exactly these same types of curvature, even though we can't easily visualize what that means. Just as a two-dimensional being on a curved surface might not immediately realize that their world is curved, we might be living in a three-dimensional space that has curvature we don't immediately perceive. This realization opens up 3 fundamental possibilities for the overall geometry of our universe. The universe could be flat, meaning it follows Euclidean geometry on the largest scales and extends infinitely in all directions. It could be closed, curving back on itself like the surface of a 4-dimensional sphere, which would make it finite in size but without any boundaries or edges. Or it could be open, curving away from itself in a hyperbolic fashion, which would make it infinite but with a very different structure than flat space. Each of these possibilities has profoundly different implications for whether space has an end. In a flat universe, space extends infinitely in all directions, meaning there's no edge or boundary to speak of. No matter how far you travel, there's always more space ahead of you. This infinite space would contain an infinite amount of matter and energy, including an infinite number of stars, galaxies, and even planets like Earth. In a closed universe, space is finite, but has no boundaries. This might sound contradictory, but think about it in terms of the surface of a sphere. The surface of Earth is finite in area, but it has no edges or boundaries. If you start walking in any direction and keep going straight, you'll eventually return to your starting location from the opposite direction. Similarly, in a closed universe, if you could somehow travel in a straight line for long enough, you would eventually return to your starting location from the opposite direction.
The closed universe scenario is particularly fascinating because it means that space, while finite, still has no edge in any meaningful sense. There's no point where space stops and something else begins. Instead, space curves back on itself, creating a cosmos that is both finite and boundaryless. This is what cosmologists mean when they talk about the universe being finite but unbounded. An open universe, with its hyperbolic geometry, would be infinite like a flat universe but would have different large-scale properties. In an open universe, space curves away from itself, creating more room than you'd expect based on flat geometry. This has implications for how structure forms and evolves over cosmic time, though the universe would still extend infinitely in all directions. Understanding these different possibilities requires us to think carefully about the relationship between the local properties of space and its global structure. Even if space is curved on the largest scales, it can appear perfectly flat over smaller regions. This is exactly what we observe in our everyday experience. The surface of the Earth appears flat to us most of the time, even though we know it's actually curved. The curvature of space is determined by the total amount of matter and energy it contains. Einstein's field equations provide a precise mathematical relationship between the curvature of spacetime and the density of matter and energy. If the universe contains exactly a certain critical density of matter and energy, space will be perfectly flat. If it contains more than this critical density, space will curve back on itself in a closed geometry. If it contains less than the critical density, space will curve away from itself in an open geometry. This critical density is incredibly small by everyday standards, only about 6 hydrogen atoms per cubic meter of space on average. To put this in perspective, the best vacuum chambers we can create on Earth still contain trillions of atoms per cubic meter of space. Yet this tiny density determines the fundamental geometry of the entire cosmos.
What makes this even more remarkable is that the curvature of space affects not just the paths that matter follows through the universe, but also the behavior of light itself. Light always follows the straightest possible path through space, but if space is curved, then what we perceive as a straight line is actually curved from the perspective of a higher dimensional observer. This leads to observable consequences that allow us to determine which type of geometry our universe actually has. In a closed universe, light rays that start out parallel will gradually converge, making distant objects appear larger than they would in a flat universe. In an open universe, parallel light rays diverge, making distant objects appear smaller. By carefully measuring the apparent sizes of objects at different cosmic distances, we can determine which type of geometry describes our space. The curvature of space also affects how the universe evolves over time. In a closed universe, the gravitational attraction of all the matter will eventually halt the expansion and cause space to contract again, leading to a big crunch that's the reverse of the Big Bang. In an open or flat universe, expansion will continue forever, though the rate of expansion depends on the exact geometry and the properties of dark energy. These different fates highlight something profound about the relationship between geometry and physics. The shape of space isn't just an abstract mathematical concept. It determines the ultimate destiny of everything in the cosmos. Whether stars will continue to shine for trillions of years or whether the universe will collapse back into a hot, dense state depends fundamentally on whether space is flat, closed, or open.
Now that we understand the 3 possible geometries that space can have, the next crucial question becomes, how can we actually measure which geometry describes our universe? This is one of the most challenging problems in observational cosmology, because we're trying to determine the shape of something that we can only observe from the inside. It's like trying to figure out whether you're living on a flat plane, a sphere, or a saddle-shaped surface when you can only make measurements from your current location. The solution to this problem requires some of the most ingenious techniques in all of science, combining Einstein's insights about the relationship between geometry and gravity with precise observations of the most distant objects we can see. Let's explore how cosmologists have managed to measure the shape of the entire universe. The first approach involves using what cosmologists call standard candles, objects whose intrinsic brightness we know, allowing us to determine their distance by measuring how bright they appear from Earth. The most important standard candles for cosmological measurements are Type A1 supernovae,
which are thermonuclear explosions of white dwarf stars that always release approximately the same amount of energy. Here's how this works. In a flat universe, the relationship between an object's distance and its apparent brightness follows a simple inverse square law. If you double the distance to an object, it appears 1/4 as bright. But in a curved universe, this relationship is modified by the geometry of space itself. In a closed universe, space curves back on itself, acting like a cosmic lens that focuses light rays. This focusing effect makes distant objects appear brighter than they would in flat space. It's similar to how a magnifying glass can make objects appear larger and brighter by bending light rays toward your eye. Conversely, in an open universe, space curves away from itself, causing light rays to diverge and making distant objects appear dimmer than they would in flat space. By measuring the brightness of many Type A1 supernovae at different distances, and comparing these measurements to what we'd expect in different geometries, cosmologists can determine which type of curvature best matches the observations. This technique has been refined over decades and has provided some of our most precise measurements of cosmic geometry. But supernovae aren't the only tool we have for measuring the shape of space. Another powerful technique involves studying the cosmic microwave background radiation that we discussed earlier. The temperature variations in this ancient light carry information about the geometry of the universe encoded in their patterns.
Think of the cosmic microwave background as a cosmic wallpaper with a subtle pattern of slightly warmer and cooler regions. The size and distribution of these patterns depend on the geometry of space. In a flat universe, acoustic waves in the early universe created temperature variations with characteristic sizes that we can calculate precisely. In a closed universe, these patterns would appear larger than expected, while in an open universe they would appear smaller. The key insight is that these patterns represent acoustic oscillations in the hot, dense plasma that filled the early universe. Just like sound waves in air, these oscillations had characteristic wavelengths determined by the physical conditions in the early cosmos. When the universe became transparent and released the cosmic microwave background, these acoustic patterns were frozen into the temperature variations we observe today. By measuring the angular size of these acoustic peaks in the cosmic microwave background, cosmologists can determine the geometry of space with remarkable precision. It's like using a cosmic ruler to measure the curvature of the universe. If space is curved, it will magnify or shrink the apparent size of these patterns in predictable ways. Modern satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory have mapped the cosmic microwave background with extraordinary precision, measuring temperature variations smaller than a millionth of a degree across the entire sky. These observations have allowed us to determine the geometry of our universe with an accuracy that would have seemed impossible just a few decades ago. The results of these measurements are both surprising and profound. Our universe appears to be remarkably flat. The curvature is so small that if it exists at all, it's barely detectable with our current instruments. This means that parallel lines remain parallel over cosmic distances. Triangles have angles that add up to exactly 180 degrees, and the familiar rules of Euclidean geometry apply even on the largest scales we can observe.
But there's an important subtlety here that we need to understand clearly. When cosmologists say the universe is flat, they're talking about the geometry of space averaged over enormous volumes.
Space can still be curved locally by the presence of matter and energy. In fact, this local curvature is what we experience as gravity. The space around the Sun is curved by the Sun's mass, and this curvature guides the Earth's orbit. Similarly, the space around our galaxy is curved by the galaxy's gravitational field. What we've measured is that when you average out all these local curvatures over volumes much larger than galaxy clusters, space appears to be flat overall. It's like looking at the surface of the ocean from an airplane. Even though there are waves and ripples at small scales, the overall surface appears perfectly flat when viewed from sufficient height. This flatness has profound implications for the question of whether space has boundaries. A flat universe that extends infinitely in all directions cannot have edges or boundaries in any conventional sense. No matter how far you travel through such a space, there's always more space ahead of you. This infinite extent means that a flat universe contains an infinite amount of matter and energy, including an infinite number of galaxies, stars, and even planets identical to Earth. However, we must be careful to distinguish between the observable universe and the universe as a whole. Even if space is infinite, we can still only observe a finite region around us, the observable universe we discussed earlier. The flatness we've measured tells us about the geometry within this observable region, but it doesn't necessarily tell us what space looks like on scales much larger than what we can observe. This distinction becomes important when we consider the possibility that space might be flat locally but still have large-scale topology that's more complex. For example, space could be flat but finite if it has a topology like a three-dimensional torus, the three-dimensional analog of a donut surface. In such a universe, space would be flat everywhere locally, but if you traveled far enough in any direction, you might eventually return to your starting point. Detecting such topological features requires looking for subtle patterns in the cosmic microwave background or other observations. If our observable universe is large enough to contain multiple copies of the same regions of space due to the wraparound topology, we might see correlated patterns in opposite directions of the sky. Several groups of researchers have searched for such correlations, but so far, the evidence suggests that if our universe has complex topology, it's larger than our current observable horizon.
The measurement techniques we've described also provide information about other fundamental properties of the universe, including its age, composition, and rate of expansion. The same observations that tell us space is flat also reveal that our universe is about 13.8 billion years old, that ordinary matter makes up only about 5% of the total energy density, and that the expansion is accelerating due to a mysterious form of energy called dark energy. These measurements represent one of the greatest triumphs of modern cosmology. Using nothing more than careful observations of light from distant objects, we've been able to determine the shape of space itself across billions of light years. We've measured the curvature of the universe to a precision of better than 1%, providing strong constraints on the fundamental nature of reality. But perhaps the most remarkable aspect of these measurements is what they suggest about the early universe. The fact that space is so perfectly flat today implies that it must have been even flatter in the past, because any initial curvature would have been amplified by billions of years of cosmic evolution. This leads us to what cosmologists call the flatness problem.
The flatness of our universe presents us with one of the most perplexing puzzles in all of cosmology, a puzzle that reveals just how special and unlikely our cosmic situation appears to be.
Understanding this flatness problem is crucial for grasping why many cosmologists believe our observable universe might be just a tiny piece of something much larger and stranger. To understand why flatness is problematic, we need to think carefully about how the curvature of space evolves over time. In the standard model of cosmology, without additional assumptions, the curvature of space tends to grow more extreme as the universe ages. If space starts out slightly curved, that curvature becomes more and more pronounced relative to the overall size of the observable universe. It's like inflating a balloon that has a small dent in it. As the balloon gets bigger, the dent becomes more and more noticeable relative to the balloon's overall curvature. Mathematically, this evolution of curvature is described by what cosmologists call the curvature parameter, usually denoted by the Greek letter omega. If omega equals exactly 1, space is perfectly flat. If omega is greater than 1, space is closed and curves back on itself. If omega is less than 1, space is open and curves away from itself. The crucial point is that omega equal to 1 represents what mathematicians call an unstable equilibrium. It's like trying to balance a pencil perfectly on its point, theoretically possible, but incredibly difficult to achieve and maintain. The slightest deviation from perfect balance and the pencil falls over. Similarly, the slightest deviation from omega equals 1 and the universe's curvature grows more and more extreme over time.
Now, here's where the problem becomes apparent. Observations tell us that omega is incredibly close to 1 today, so close that our most precise measurements can't detect any deviation from perfect flatness. But if omega is so close to 1 today, after 13.8 billion years of cosmic evolution, it must have been extraordinarily precisely equal to 1 in the early universe. Let's put some numbers on this to appreciate just how precise this initial condition must have been. For the universe to appear as flat as it does today, the initial value of omega must have differed from exactly 1 by no more than about 1 part in 10 to the power 60. To put this in perspective, this is like aiming for a target the size of a single proton and hitting it from a distance of billions of light years. This level of precision is so extreme that it strains our credulity. In almost every other area of physics, when we encounter such incredibly specific initial conditions, it's a sign that we're missing some important physical mechanism that naturally produces those conditions. It's like finding that every grain of sand on every beach on Earth has exactly the same size. Theoretically possible, but so unlikely that you'd immediately start looking for some process that could create such uniformity. The flatness problem becomes even more severe when we consider what would have happened if the initial conditions had been even slightly different. If omega had started out even a tiny bit greater than 1, the universe would have quickly collapsed back on itself in a big crunch, never lasting long enough for stars and galaxies to form. If omega had started out even a tiny bit less than 1, the universe would have expanded so rapidly that matter never would have had a chance to clump together and form any structures at all. In other words, the narrow range of initial conditions that allows for a universe like ours, one that lasts long enough for complexity to emerge but doesn't expand so fast that nothing interesting can happen, is extraordinarily small. This fine-tuning problem suggests that either we're incredibly lucky to find ourselves in such a special universe, or there's some physical mechanism that naturally produces these special initial conditions.
This is where cosmic inflation comes to the rescue once again. Remember that inflation involves a period of exponential expansion in the very early universe, when space grew from smaller than a proton to larger than a grapefruit in an infinitesimally small fraction of a second. This incredible expansion has a remarkable effect on the curvature of space. To understand how inflation solves the flatness problem, let's return to our balloon analogy. Imagine you have a balloon with all sorts of wrinkles, dents, and curves on its surface. Now imagine inflating this balloon to enormous size, perhaps to the size of the Earth. As the balloon expands, those wrinkles and curves get stretched out and become less and less noticeable. From the perspective of an ant crawling on the inflated balloon, the surface appears perfectly smooth and flat, even though the balloon as a whole retains its overall curved shape. Cosmic inflation works in exactly the same way. Any initial curvature that space might have had gets diluted and stretched out by the enormous expansion. After inflation, space appears perfectly flat over the scales that we can observe, even if it might have significant curvature on much larger scales that extend far beyond our observable horizon. This inflationary solution to the flatness problem is elegant and compelling, but it comes with profound implications for the nature of space and its extent. If inflation is the correct explanation for why our observable universe appears so flat, then our observable region represents just a tiny patch of flat space within a much larger structure that might have very different properties on larger scales. Think about what this means. If you could somehow zoom out far enough from our observable universe, you might see that it's embedded in a larger space with significant curvature, complex topology, or even regions with different physical laws. Our flat patch would be like a small section of a vast and complex cosmic landscape, most of which remains forever beyond our ability to observe.
The flatness problem also connects to deeper questions about the nature of time and causality in the early universe. The fact that such precise initial conditions seem to be required for a universe like ours to exist raises questions about what determined those conditions. Was there some earlier epoch that set up the initial state for our Big Bang? Are there physical processes that naturally produce the kinds of initial conditions that lead to inflation? Some versions of inflation theory suggest that the inflationary process might never completely end everywhere. Instead, inflation might continue in some regions while ending in others, creating a vast multiverse of inflated regions with different properties. In this scenario, our observable universe would be just one bubble in an infinite cosmic foam, with new bubbles constantly being created as inflation continues in other regions. This eternal inflation scenario has fascinating implications for the question of where space ends. If inflation can create an infinite amount of space, then the question of boundaries becomes even more complex. There might be regions of space that are still inflating, regions that have finished inflating and evolved into complex structures like our observable universe, and regions that are just beginning their inflationary expansion. The flatness problem thus serves as a window into some of the deepest questions in cosmology. It reveals that our universe's basic properties, the ones that make stars, galaxies, planets, and life possible, depend on incredibly precise conditions that seem to require some kind of explanation. The fact that inflation provides such an explanation is one of the strongest pieces of evidence supporting inflationary cosmology. But the flatness problem also highlights the provisional nature of our current understanding. While inflation elegantly solves the flatness problem, it raises new questions about what caused inflation, what determines the properties of the inflaton field that drives it, and whether inflation is truly the correct explanation for the conditions we observe.
These questions push us to consider possibilities that extend far beyond our current observational capabilities. They suggest that understanding the true nature of space, including whether it has boundaries and what might lie beyond those boundaries,
might require us to develop new theoretical frameworks and new ways of thinking about the relationship between observation and reality. The journey from measuring the geometry of space to understanding the implications of that geometry reveals something profound about the scientific enterprise itself. We begin with careful observations of distant supernovae and ancient light, use those observations to infer the shape of space itself, and end up confronting questions about the ultimate nature of reality that push the boundaries of physics and philosophy. This progression from observation to theory to speculation illustrates both the power and the limitations of our scientific understanding. We can measure the geometry of space with extraordinary precision, but the implications of those measurements lead us into territories where direct verification becomes impossible and where our theories must be evaluated more on their elegance, consistency, and ability to solve multiple problems simultaneously.
We've now reached perhaps the most profound and mind-expanding part of our journey into the question of where space ends. Everything we've discussed so far has been based on things we can actually observe, measure, and test through scientific methods. But now we must venture into territory that pushes the very boundaries of what science can tell us, the vast realm of space that lies forever beyond our ability to observe directly. To understand what might exist beyond our observable universe, let's start by making sure we have a crystal clear picture of what beyond actually means in this context. When we talk about the observable universe, we're describing a sphere centered on Earth with a radius of about 46.5 billion light-years. This represents the farthest distance from which light has had time to reach us since the Big Bang, accounting for the expansion of space during the light's journey. But here's the crucial point that we need to grasp fully. This observational boundary is not a physical edge or wall in space itself. It's simply the limit of what we can see from our particular location in the cosmos. Think of it like being in the middle of a vast dark forest on a foggy night with a flashlight that can illuminate objects only within a 100-meter radius. The fact that you can't see beyond that 100-meter circle doesn't mean the forest ends there. It just means that your ability to gather information is limited by the range of your flashlight and the density of the fog. The cosmic situation is remarkably similar, except that our flashlight is the finite speed of light, and our fog is the finite age of the universe combined with cosmic expansion. Just as the forest almost certainly continues beyond the reach of your flashlight beam, space almost certainly continues far beyond the boundary of our observable universe. Now, let's think carefully about what this means. If cosmic inflation really occurred the way we believe it did, then the region that became our entire observable universe was once smaller than a proton and was inflated to enormous size during that brief period of exponential expansion. But inflation wouldn't have affected only the tiny region that became our observable universe. It would have inflated a much larger volume of space simultaneously.
To get a sense of the scales involved, consider this remarkable calculation. If our entire observable universe represents the inflated version of a region that was originally about the size of a proton, then the total inflated region would be vastly larger than what we can observe. Some estimates suggest that the unobservable universe, the part of space that underwent the same inflationary expansion as our observable region but lies beyond our cosmic horizon, could be at least 10 to the 23 times larger than what we can see. Let me help you visualize just how enormous this number is.
If our observable universe were shrunk down to the size of a single atom, the total inflated region would still be larger than Earth. If we shrunk our observable universe down to the size of a grain of sand, the total inflated region would be larger than our entire solar system. This comparison illustrates that we might be living in just an infinitesimally small patch of a vastly larger cosmic structure. But what would this unobservable region actually look like? This is where we encounter one of the most fascinating aspects of cosmological thinking. The laws of physics that operate in our observable universe should apply equally well throughout the inflated region that lies beyond our horizon. This means that the unobservable universe should contain the same types of fundamental particles, follow the same physical laws, and exhibit the same basic processes that we observe in our own cosmic neighborhood. However, while the fundamental laws remain the same, the specific outcomes of various processes could be very different in different regions. Remember that the tiny quantum fluctuations that existed before inflation were stretched to cosmic scales and became the seeds for all the structure we see today: galaxies, galaxy clusters, and the vast web of cosmic architecture that spans our observable universe. But these quantum fluctuations were random, which means that different regions of the inflated space would have started with different patterns of these fluctuations.
This randomness has profound implications for what the unobservable universe might contain. In regions where the initial fluctuations happen to be slightly different from those in our observable universe, the pattern of galaxy formation, the distribution of matter and energy, and even the detailed history of cosmic evolution could unfold in dramatically different ways. For instance, there might be regions where the initial fluctuations were stronger than average, leading to the formation of much more massive structures than anything we see in our observable universe. There could be regions where supermassive black holes formed much earlier and grew much larger, fundamentally altering the evolution of galaxies in those areas. Conversely, there might be regions where the initial fluctuations were weaker, leading to a much more uniform distribution of matter and very different patterns of star and galaxy formation. The implications become even striking when we consider that if the unobservable universe is truly vast, then it must contain regions with every possible variation of initial conditions that quantum mechanics allows. This means there would be regions that are nearly identical to our observable universe, regions that are completely different, and every possible variation in between. In fact, if the unobservable universe is large enough, it would contain exact copies of our observable universe, including exact copies of our galaxy, our solar system, and even exact copies of Earth, with exact copies of every person who has ever lived. This isn't science fiction or wild speculation. It's a direct logical consequence of combining quantum mechanics with a sufficiently large volume of space that follows the same physical laws as our observable region.
To understand why this must be true, consider that quantum mechanics tells us there are only a finite number of possible configurations for any given volume of space, even though that number is astronomically large. If you have an infinite amount of space, or even just a sufficiently large finite amount, then every possible configuration must occur not just once, but infinitely many times. It's like having an infinite number of coin flips. Not only will you get every possible sequence of heads and tails, but you'll get each sequence infinitely many times. This realization leads to one of the most mind-bending consequences of modern cosmology. There are almost certainly countless versions of you reading these exact words right now in other regions of the unobservable universe. There are versions making slightly different choices, versions living in worlds where history unfolded differently, and versions experiencing lives that are similar to yours in some ways, but radically different in others. Some of these copies of you exist in regions where the fundamental constants of physics are slightly different. Perhaps gravity is a bit stronger or weaker, or the electromagnetic force has a slightly different strength. These differences would lead to universes where stars burn differently, where planets form under different conditions, and where the entire history of cosmic evolution follows alternative pathways. But let's step back for a moment and consider what it means to talk about these unobservable regions. By definition, we can never directly observe or communicate with anything that lies beyond our cosmic horizon. This raises profound questions about the nature of scientific knowledge and the difference between what we can know and what we can verify through observation.
In most areas of science, we can test our theories by making predictions and then checking whether those predictions match observations. But when we talk about the unobservable universe, we're venturing into territory where direct empirical verification is impossible in principle, not just in practice. We can never send a probe to these distant regions, never receive a signal from them, and never gather direct evidence about their properties. This might make it seem like speculation about the unobservable universe is purely philosophical rather than scientific. However, there's an important distinction to be made here. While we cannot directly observe these regions, our theories about them are not arbitrary speculation. They're based on extending our best-tested physical theories, general relativity, quantum mechanics, and our understanding of cosmic inflation beyond the boundaries of our observable universe. These theories have been tested extensively within our observable universe and have passed every test we've been able to devise. When we use these same theories to predict what exists beyond our cosmic horizon, we're not making wild guesses, we're following the logical implications of our most successful scientific theories. Moreover, some aspects of the unobservable universe do have indirect observational consequences that we can test. For example, the uniformity of the cosmic microwave background radiation provides evidence that our observable universe was once in causal contact with regions that are now far beyond our horizon. The patterns of temperature fluctuations in the CMB also provide information about the statistical properties of the quantum fluctuations that must exist throughout the larger inflated region. Still, we must acknowledge that our understanding of the unobservable universe involves a level of theoretical inference that goes well beyond what we can directly verify. This pushes us to think carefully about the relationship between scientific knowledge and empirical evidence. How confident can we be in theories that make predictions about regions we can never observe? What does it mean for something to be scientifically meaningful if it can never be directly tested?
These questions don't have easy answers, but they highlight something important about the nature of cosmological thinking. When we try to understand the universe as a whole, including parts we can never observe, we necessarily venture beyond the realm of direct empirical verification and into the domain of theoretical inference and mathematical reasoning. This doesn't make such thinking unscientific, but it does require us to be careful about the level of confidence we place in our conclusions. We can be quite confident that some form of unobservable universe exists beyond our cosmic horizon, because this follows naturally from our well-tested theories about cosmic inflation. We can be less confident about the specific details of what these regions contain, because those details depend on assumptions about initial conditions and other factors that we cannot directly measure. Understanding the unobservable universe also changes our perspective on the question of where space ends. If space extends far beyond what we can observe, then the boundary of the observable universe is not a boundary of space itself, but simply a boundary of our knowledge.
Space might continue infinitely beyond our horizon, or it might have boundaries or structures that exist on scales so vast that they dwarf even the unobservable regions we've been discussing. This realization is both humbling and inspiring. It's humbling because it reminds us that our observable universe, vast as it seems to us, might just be an infinitesimally small part of a much grander cosmic structure. But it's also inspiring because it opens up possibilities for understanding that extend far beyond our current observational capabilities, challenging us to develop new ways of thinking about reality and our place within it.
Now we venture into even more extraordinary territory as we explore what might happen if cosmic inflation, that period of exponential expansion in the early universe, never completely stops everywhere. This idea, known as eternal inflation, leads us to one of the most mind-expanding concepts in all of cosmology, the multiverse. Understanding this possibility is crucial for grasping just how complex and vast the answer to "where does space end" might actually be. Let's start by examining more carefully what we mean when we say that cosmic inflation ended. In our observable universe, inflation lasted for only an extremely brief period, perhaps 10 to the minus 32 seconds, before it transitioned to the more sedate expansion that characterizes the universe we observe today. During inflation, space was dominated by a special kind of energy field called the inflaton field, which drove the exponential expansion. When this field decayed and converted its energy into ordinary matter and radiation, inflation ended and the hot Big Bang phase of evolutionary cosmology began. But here's the crucial insight that leads to eternal inflation. While the inflaton field decayed in our region of space, there's no fundamental reason why it must have decayed everywhere simultaneously. In fact, quantum mechanics tells us that the decay process itself should be probabilistic and random, occurring at different times in different locations throughout the inflating space. To understand this better, imagine a vast field of popcorn kernels being heated. Some kernels will pop early, some will pop later, and at any given moment, there will be regions where popping has occurred alongside regions where kernels are still heating up and haven't popped yet. Similarly, in eternal inflation, some regions of space undergo the transition from inflation to normal expansion early, while other regions continue inflating for much longer periods. This analogy helps us visualize what eternal inflation looks like, but the reality is far more dramatic than popcorn. In regions where inflation continues, space keeps expanding exponentially, doubling in size every 10 to the minus 37 seconds or so. This means that the volume of inflating space grows so rapidly that even though some regions are constantly transitioning out of inflation, the total amount of inflating space continues to increase without bound.
Here's where the mathematics becomes truly staggering. Even if only a tiny fraction of space remains in the inflating phase at any given moment, the exponential expansion means that this tiny fraction quickly becomes larger than all the regions that have transitioned out of inflation combined. It's like having a population where individuals are constantly being born at an exponential rate. Even if many individuals die, the overall population continues to grow explosively. This process creates what cosmologists call a multiverse, a vast collection of pocket universes or bubble universes, each representing a region where inflation ended and normal cosmic evolution began. Our entire observable universe would be just one such bubble in this infinite cosmic foam, surrounded by other bubbles with their own histories, structures, and possibly even different physical laws governing how matter and energy behave. Let me help you visualize this multiverse structure.
Imagine an enormous block of Swiss cheese that's constantly growing as more holes appear and existing holes expand. Each hole represents a bubble universe like ours, while the cheese itself represents the regions that are still undergoing inflation. The cheese grows so fast that even as new holes keep appearing, there's always more cheese than holes, and the whole structure keeps expanding without any limit. Each bubble universe in this multiverse would have its own Big Bang event, the moment when inflation ended in that particular region and converted the inflaton field's energy into ordinary matter and radiation. From the perspective of observers within any given bubble, this would appear to be the beginning of their universe, just as the Big Bang appears to be the beginning of our universe from our perspective. But the properties of each bubble universe might be quite different from our own. The process by which inflation ends and the inflaton field decays can occur in many different ways, potentially leading to different values of fundamental constants, different numbers of spatial dimensions, different types of particles, and even different physical laws governing how matter and energy behave.
For instance, in some bubble universes, the electromagnetic force might be stronger or weaker than in our universe, leading to atoms with different properties and chemistry that follows different rules. In others, gravity might be dramatically stronger, causing stars to burn much faster and galaxies to form very different structures. Some bubbles might have extra dimensions of space that are much larger than the tiny, curled-up extra dimensions that string theory predicts in our universe. Even more dramatically, some bubble universes might have completely different numbers of dimensions, perhaps two-dimensional universes that exist on cosmic surfaces, or four-dimensional universes where space has 4 rather than 3 dimensions. The physics in such universes would be so different from our own that we can barely imagine what structures might form or what kinds of complexity might emerge. This variation in physical laws and constants arises from the quantum nature of the fields that drive inflation and determine the properties of each bubble universe. Just as quantum mechanics introduces randomness into the decay of radioactive nuclei, it introduces randomness into the process by which inflation ends and the fundamental properties of each resulting bubble universe are determined. The implications of this eternal inflation scenario are profound and far-reaching. If eternal inflation is correct, then our universe, with its specific values of physical constants, its particular history of cosmic evolution, and all the complexity that has emerged within it, represents just one possibility among an infinite number of alternatives. Every possible way that the laws of physics could be configured, every possible history that cosmic evolution could follow, and every possible outcome of quantum processes would be realized somewhere within the infinite multiverse. This leads to what philosophers and cosmologists call the principle of mediocrity taken to its ultimate extreme. Not only are we not at the center of our galaxy or our universe, but our entire universe might be just one unremarkable bubble in an infinite collection of bubble universes, most of which are probably very different from our own. But the multiverse raises challenging questions about the nature of scientific explanation and prediction. In our universe, we're accustomed to using the apparent fine-tuning of physical constants. The fact that they seem precisely adjusted to allow for the existence of stars, planets, and life as a guide for developing theories about fundamental physics. If these constants had been even slightly different, our universe would be a cold, empty place where no interesting structures could form. However, in an infinite multiverse, every possible value of these constants would be realized somewhere. This means that the apparent fine-tuning of our universe might not require any special explanation. We simply find ourselves in one of the bubble universes where the constants happen to have values that allow for complexity and life, because those are the only types of universes where observers like us could exist to wonder about fine-tuning in the first place. This reasoning, known as the anthropic principle, suggests that some questions about why our universe has the properties it does might not have deep physical answers. Instead, the answer might simply be that we observe these properties because we couldn't exist in a universe where they were significantly different. It's like asking why you were born in a city rather than in the middle of the ocean. The answer isn't that there's something special about cities that makes them preferred locations for human birth, but simply that humans can only survive and thrive in certain environments. The anthropic reasoning becomes particularly important when we consider the question of how typical or special our bubble universe might be within the larger multiverse. If most bubble universes are empty and lifeless because their physical constants don't allow for the formation of complex structures, then bubble universes like ours might be extremely rare. We might be living in a tiny oasis of complexity within a vast desert of empty, sterile space.
Alternatively, if there are many different ways that physical constants can be adjusted to allow for interesting structures and potentially life, then our bubble universe might be relatively typical among the subset of bubbles where observers can exist. Determining which of these scenarios is correct would require understanding both the statistics of how different physical constants are distributed among bubble universes and the range of constants that can support complex structures. These questions push us to the very limits of what we can meaningfully discuss using scientific methods. By definition, we cannot directly observe other bubble universes or communicate with them. The regions of space that are still inflating between the bubbles are expanding so rapidly that no signal from one bubble can ever reach another bubble. Each bubble universe is fundamentally isolated from all the others, making direct empirical verification of the multiverse hypothesis impossible. Yet the multiverse isn't pure speculation disconnected from observational evidence. The basic mechanism of eternal inflation follows naturally from our understanding of quantum field theory and cosmic inflation, both of which have strong observational support within our own universe. The patterns we observe in the cosmic microwave background provide evidence that our universe did undergo a period of inflation, and quantum mechanics tells us that this inflationary process should naturally lead to the eternal inflation scenario. Moreover, some versions of multiverse theory make predictions about the statistical properties of physical constants that we might be able to test by making more precise measurements within our own universe. For example, if our universe is typical among bubble universes that can support observers, then the values of fundamental constants should neither be extremely fine-tuned for life nor completely random, but should fall within certain predicted ranges. The multiverse also provides a new perspective on the question of where space ends. In an eternally inflating multiverse, space never stops growing. It continues expanding exponentially in the regions between bubble universes, constantly creating new volume and new possibilities for additional bubbles to form. This suggests that space, at least in some regions, continues infinitely and without any boundaries or edges.
However, the structure of this space is far more complex than the simple, infinite expanse we might have imagined. Instead of uniform, empty space extending infinitely in all directions, we have a dynamic, ever-growing network of inflating regions punctuated by bubble universes, each with its own physics, history, and possibilities for complexity and life. Understanding this multiverse structure requires us to think about space and time in new ways. From the perspective of observers within any given bubble universe, space appears to have the familiar three dimensions. Time flows in a particular direction, and the universe has a definite age and history stretching back to its Big Bang. But from a larger perspective that encompasses the entire multiverse,
Space and time have a much richer and more complex structure that connects different bubble universes through the inflating regions between them. This complexity suggests that the question, where does space end, might not have a simple answer, even in principle. Instead of space having a single, well-defined boundary, we might have a fractal-like structure where space contains bubbles within bubbles, regions with different dimensionalities, and connections between different parts of the multiverse that we can barely imagine.
As we delve deeper into the implications of eternal inflation and the multiverse, we encounter one of the most technically challenging and philosophically profound problems in modern cosmology, the measure problem. This problem strikes at the heart of how we can make any meaningful predictions or statements about an infinite multiverse, and understanding it is crucial for grasping both the power and the limitations of multiverse theories. The measure problem arises from a simple but devastating observation. In an eternally inflating multiverse, everything that can happen does happen, and it happens infinitely many times. This creates a mathematical and conceptual nightmare for anyone trying to calculate probabilities or make predictions about what we should expect to observe in such a universe. Let me illustrate the problem with a concrete example. Suppose you want to calculate the probability that, in our universe, the first star to form had a mass exactly equal to that of our Sun. In a normal, finite universe, you might approach this by calculating how many stars formed throughout cosmic history and determining what fraction of them had the specified mass. This would give you a probability between 0 and 1, and you could compare this prediction to observations. But in an infinite multiverse, there are infinitely many bubble universes, and therefore infinitely many first stars. Among these infinite first stars, infinitely many will have masses equal to our Sun's mass, infinitely many will have different masses, and infinitely many will fall into any other category you might specify. When you try to calculate the probability by taking the ratio of favorable outcomes to total outcomes, you get infinity divided by infinity, a mathematical expression that has no well-defined value. This problem extends to every possible question you might want to ask about the multiverse. What's the probability that a randomly selected bubble universe contains galaxies? Infinity divided by infinity. What's the probability that it contains life? Infinity divided by infinity. What's the probability that its physical constants allow for the existence of atoms? Again, infinity divided by infinity.
The measure problem thus threatens to render the entire multiverse framework scientifically meaningless. If you can't calculate probabilities or make predictions, then how can you test whether the multiverse hypothesis is correct? How can you determine whether our observations are consistent with what we should expect in an infinite multiverse? To understand why this problem is so challenging, we need to think carefully about what it means to select a typical or random bubble universe from an infinite collection. In finite collections, we have well-established ways of defining what we mean by random selection. Every item in the collection has an equal probability of being chosen. But when dealing with infinite collections, this approach breaks down because there's no unique way to define what randomly selected means for an infinite collection. This isn't just a technical mathematical issue, it reflects a deep conceptual problem with how we think about infinite collections. Consider the following thought experiment. Imagine an infinite row of boxes, each containing a number. Some boxes contain positive numbers, some contain negative numbers, and some contain 0. Now, suppose someone asks you to calculate the probability that a randomly selected box contains a positive number.
The problem is that there's no unique way to define what randomly selected means for an infinite collection. You could select boxes by choosing every 10th box or every 100th box, or by using any number of other selection procedures. Different selection procedures can give you different answers for the probability you're trying to calculate. Without a natural preferred way to select from the infinite collection, the notion of probability becomes ambiguous. The same issue arises in eternal inflation. There are infinitely many bubble universes forming at every moment, and there's no natural way to define what it means to select a typical bubble or assign probabilities to different types of bubbles. Any answer you get depends on the specific mathematical procedure you use to handle the infinities, and different procedures can give you different answers.
Cosmologists have proposed several approaches to solving the measure problem, each with its own advantages and difficulties. One approach, called the proper time cutoff, involves stopping the eternal inflation process at some specified time and only considering the bubble universes that have formed by that time. This creates a finite collection that you can work with mathematically, but it introduces an arbitrary cutoff that seems unphysical. Another approach, called the scale factor cutoff, involves stopping the counting process when the inflating regions have expanded by some specified amount. This approach has the advantage of being based on a physical quantity, the scale factor describing the size of inflating regions, but it still introduces an arbitrary cutoff that affects the final results. A third approach, known as the stationary measure, attempts to sidestep the infinity problem by focusing on the rate at which different types of bubble universes are produced, rather than their total numbers. This approach can sometimes give well-defined answers, but it requires making assumptions about the detailed physics of the inflation process that we can't directly test. Each of these approaches can give different predictions for what we should expect to observe in our universe, which makes it difficult to test whether eternal inflation is correct. For example, some measures predict that most observable universes should have very different physical constants from our own, while others predict that universes like ours should be relatively common among observable universes. The measure problem also raises deep questions about the relationship between physical reality and mathematical description. If physical reality consists of an infinite multiverse where everything possible happens infinitely many times, then the mathematical tools we use to describe this reality must be capable of handling these infinities in a meaningful way. But as we've seen, our current mathematical framework doesn't provide a unique, unambiguous way to deal with infinite collections of universes. This suggests that solving the measure problem might require developing new mathematical tools or new ways of thinking about probability and statistical inference in infinite systems. Some researchers have explored approaches based on algorithmic information theory. Others have investigated connections to measure theory in mathematics. And still others have proposed that the problem might require a fundamental revision of how we think about the relationship between observation and reality. But the measure problem isn't just a technical challenge for theorists. It also has profound implications for how we interpret our own existence and observations. If we live in an infinite multiverse where everything possible happens infinitely often, then what does it mean to say that our universe or our existence is probable or improbable? Some philosophers and cosmologists have argued that in an infinite multiverse, the concepts of probability and typicality lose their meaning entirely. If there are infinitely many versions of you reading these words, infinitely many versions making different choices, and infinitely many versions living in universes with different histories, then what sense does it make to ask whether your particular experiences are likely or unlikely? Others have suggested that we need to fundamentally revise our understanding of what it means to make scientific predictions in an infinite multiverse. Instead of asking about probabilities, we might need to ask about the relative densities or measures of different types of observations, or we might need to focus on questions that can be answered without reference to infinite collections. The measure problem also connects to broader questions about the nature of scientific explanation and the role of theory in physics. Traditional scientific theories make specific, testable predictions about what we should observe under particular circumstances. But if eternal inflation is correct and the measure problem can't be definitively resolved, then the theory might not be able to make the kind of sharp, testable predictions that we're used to expecting from successful physical theories.
This doesn't necessarily mean that eternal inflation is wrong or unscientific, but it does suggest that we might need to develop new criteria for evaluating theories that make claims about infinite systems. We might need to focus more on the internal consistency and elegance of theories, their ability to explain multiple observed phenomena simultaneously, and their connections to other well-tested areas of physics. The measure problem thus serves as a window into some of the deepest questions in the philosophy of science. What does it mean for a scientific theory to be meaningful if it can't make unique, testable predictions? How should we evaluate theories that posit the existence of infinitely many unobservable entities? What role should mathematical elegance, explanatory power, and theoretical unity play in theory selection when direct empirical testing becomes impossible? These questions don't have easy answers, but they highlight the remarkable intellectual journey that the study of cosmology has taken us on. We began with the simple question of where space ends, and we've arrived at deep philosophical questions about the nature of infinity, probability, and scientific knowledge itself. The measure problem reminds us that even our most sophisticated theories about the universe can lead us into territory where the conventional tools of scientific reasoning become strained or inadequate. This doesn't diminish the value of these theories, but it does require us to be honest about their limitations and to continue working on the conceptual and mathematical frameworks needed to fully understand their implications. Moreover, the measure problem illustrates something important about the relationship between theoretical physics and observable reality. While we may never be able to directly observe other bubble universes or test the detailed predictions of eternal inflation, the conceptual framework that leads to these ideas, quantum field theory, general relativity, and cosmic inflation, has been extensively tested and confirmed within our observable universe.
The measure problem thus represents both a challenge and an opportunity for cosmology. It's a challenge because it prevents us from making the kind of sharp predictions that would allow us to definitively test multiverse theories. But it's also an opportunity to develop new mathematical tools, new conceptual frameworks, and new ways of thinking about the relationship between theory and observation that might prove valuable for understanding other aspects of physics and cosmology. As we continue to grapple with these deep questions, we should remember that science has faced conceptual challenges before that initially seemed insurmountable. The development of quantum mechanics required physicists to abandon classical notions of determinism and objective reality. The development of relativity required abandoning absolute notions of space and time. Perhaps understanding the true nature of space and its extent will require similar conceptual leaps that we can't yet imagine.